Diagnosing illness today requires the trained eye of a doctor. With machine learning, we might someday be able to diagnose illnesses using only data sets and algorithms. Today on Software Engineering Daily, we are joined by David Kale, a researcher at the intersection of machine learning and clinical data. We discuss the machine learning and research techniques that he is using to diagnose illnesses using neural networks. And we also talk about the challenges of performing data science in hospitals, where the data is mostly confidential. After a short break from the sponsors who keep Software Engineering Daily in good health, we will get to this fascinating conversation with hospital data and machine learning researcher David Kale. As a software engineer, you have tremendous leverage in the employment market. Every company needs software engineers, and these companies are all competing for you, the engineer, a scarce resource. But as an individual engineer, you don't have much insight into this incredibly opaque market. That's where Hired.com comes in. Hired.com assigns you a talent advocate who works to understand your needs and works to find you the perfect job. Go to Hired.com/SEDaily to try out the platform today and get a $2,000 bonus if you find a job. The companies on Hired compete for you, the engineer, and they make bids to win your talent. These are companies like Facebook and Uber, companies that we know are on the cutting edge of engineering because they've come on Software Engineering Daily to talk about their tech stack. I've used Hired personally, and I've experienced firsthand the ease of finding a well-paid, enjoyable job. This was way better than replying to LinkedIn messages from uninformed recruiters, and it was also certainly better than using a job search engine. To find a great job and support Software Engineering Daily, go to hired.com/SEDaily and get a $2,000 bonus upon finding a job. Check it out. It would support the show. Now let's get on with the show. David Kale is a PhD student in computer science and an author on several papers at the intersection of machine learning and clinical data. David, welcome to Software Engineering Daily.
Hi, Jeff. How are you?
I'm doing great. It's a pleasure to talk to you.
I'm really excited about this.
Yeah, absolutely. You know, I have some background in biology and computer science. I did really bad in university at both of them, but I have some, basic understanding of both of them. So hopefully this will be an engaging conversation. From 2009 to 2012, you worked as the lead data scientist at the Children's Hospital of Los Angeles. What kind of work does a data scientist at a children's hospital do?
So that's a great question. What does a data scientist do at a hospital? And I should say that I haven't worked as a data scientist at a hospital for the last 3 years. I've been a PhD student, so it's changed a lot. The role of the data scientist at CHLA has changed a lot since I left, and changed a lot while I was there, and it's quite different in other places. But generally, because of the wealth of data that hospitals are collecting in electronic health records, there's sort of this growing sense that there's a lot of value in that data, and that we should be able to learn from that. So classically, what a statistician or sort of a data person at a hospital might do is they would be responsible for facilitating retrospective clinical studies. So doctor comes and says, I need you to pull this data for these patients from the database, and then dump it out and put it in a spreadsheet for me, and then I can run this regression analysis and publish a paper. Increasingly, what you're starting to see is people being hired to do stuff that looks a lot more like the type of data mining or machine learning work that gets done in industry and other places, where the idea is you have questions, you have a lot of rich data, you want to use that data to answer those questions. At CHLA, when I was first hired there really was no sort of set role for that. In fact, my job title at that time was software engineer. I wasn't even a data scientist. They invented that job title for me in my last year. But my mandate was, let's pull out data from the pediatric ICU. I was working within doctors who worked in the pediatric intensive care unit in a lab called the Laura P. and Leland K. Whittier virtual pediatric intensive care unit. And the vision of the VPICU, which was founded by Randall Wetzel, is to build the learning healthcare system. So that every time we have a patient that we encounter and they're sick, a treatment is delivered, and then we observe an outcome, we would like the system as a whole to learn from that outcome and get slightly better based on what we saw, the data that we collected during that. And this is not a realized vision. The doctors who treated that patient probably learn from it. Maybe the department learns from it. The hospital might learn from it if they do some kind of quality study to look at performance in the ICU from the last couple of years. But there really isn't this vision that every time a patient comes into a hospital in the United States and then they get discharged, that information and knowledge gets distributed everywhere through sharing of data, but also through maybe some kind of machine learning and a shared sort of predictive model that a lot of hospitals could be using that's learning from millions of patients being seen at different hospitals. So that was the vision. A more mundane scale, my job was to try and push the ball down the field a couple yards in that direction. So early on, I was spending a lot of time just trying to navigate the EHR systems, find data, understand data schema, organize data, process it into a form we could do some machine learning. Toward the end of my stay there, I actually did a machine learning project where I performed a clustering of 10,000 pediatric ICU patients. And this work was published in a paper at the ACM International Health Informatics Conference in 2012. And the sort of what we found was that when we clustered patients just based on sort of their vital signs and lab tests, that we found high mortality and low mortality clusters, that mortality was not uniformly or randomly distributed, that there was clearly some connection between the patterns in the patient's data and the outcomes the patients were getting, that looking at vital signs and stuff could tell us sort of within the first 24 hours could tell us whether these patients were actually going to have a good outcome or a bad outcome. And this is without using mortality as a signal, without doing supervised learning. So that was a great sort of preliminary proof of concept project. And then shortly after that was published, that's when I got admitted to PhD programs and left. But that's the kind of work increasingly you're seeing people with my skill set being hired at hospitals or being asked to do. We've got EHR data. There's a couple doctors who have visions for clinical problems they'd like to solve, and they would like to use advanced techniques that are able to handle sort of the large amount of really, really complex data. And they want people who have some idea, have ideas about how to solve and the skill set to solve those problems or answer those questions using the data. And in particular, there's sort of this feeling that we'd like to move beyond classic clinical informatics techniques, which are basically all regression based. So that's kind of what my job was like there.
So coming back to the idea of there's this disparity between what you said, the ideal world of how a hospital's feedback and improvement loop would work versus the actual reality. And there's this huge delta there. Ideally, we would have some data access, some easy data access, perhaps open data access that data scientists could use to mine and learn about patients, and the type of work that you're doing today is obviously making strides on proving the worth of that sort of approach, like exactly how important it is to get this going. I mean, we talk about the unreasonable effectiveness of recurrent neural networks, but perhaps really showing people the reality of how important and how much real world benefit we can get out of applying those things to domains like health could really shift the dial on making some progress towards this stuff. And I want to get into your work, your scientific work, but
sure.
First I want to touch a little more on what causes that delta between where we could be with this stuff and where we actually are? Is it I always hear about HIPAA and just when entrepreneurs or software engineers go into a hospital and try to propose something to some hospital bigwig, they just instantly go up against bureaucracy and slowness and cynicism. And so I'm curious, how much of it is embedded in the actual policies and how much of it is cultural, and how do we move beyond this delta?
Sure, that's an excellent and very insightful question. You're cutting to the heart. So let's start with HIPAA. HIPAA certainly, I have two perspectives on this. Certainly, HIPAA puts up some barriers, and there are a lot of other countries that you could go into, especially ones with sort of more with with kind of government managed healthcare systems that are a little more top down managed and unified. Certainly, what you would find is maybe a little more access and a little more openness, or the opposite, on the other end of the spectrum, places that are not heavily regulated, where they don't care about patient privacy. It would be easier to go to a hospital as a researcher and say, you have some data, and the doctor would just hand it to you and you'd walk out. That said, Dr. Wetzel, my boss at Children's Hospital when I was there, I think his take on this was actually correct. What he would say about HIPAA was HIPAA does not actually present real meaningful barriers to sharing data and doing research and doing sort of informatics type stuff with it. That it really actually provides a structure within it which it's not that hard to share data if you actually want to and you're willing to do it and you're willing to put in the effort. When you look at sort of the requirements for anonymization and privacy, they're pretty light. It's things like remove last name, remove social security number, remove zip code, that kind of stuff, those kinds of identifiers. The thing we've learned from like the attempt to do a second Netflix competition is that in no way, shape, or form guarantees anonymization. It's incredibly easy to re-identify people if you have enough rich data. Like as an example with a patient record would be, within an ICU, your average stay is probably 1 to 2 days, but you may have patients who have some really complicated chronic condition who might be in there for months or, like an even longer period of time, have a really long hospitalization. Well, you're only going to have a couple patients like that at the hospital. And if you ask any doctor, if you have an anonymous data set and you ask any doctor, hey, who's this patient with this length of stay of 4 months? The doctor will be like, oh yeah, I remember that guy from a couple years ago. And there's a good chance that the family, certainly the family would know who that patient is. And there's a good chance that the family's friends and everyone on their Facebook feed would know that those people had a kid or a family member who was in the hospital for 4 months. So like, it's not that so the requirements for anonymization and de-identification in HIPAA are not that bad. It could be the penalties that a hospital could get for violating HIPAA are pretty severe. So that will make bureaucrats and administrators who are risk averse shy away from sharing data and be moved very cautiously. But in general, most of the barriers I found are cultural and institutional. There's within medicine, there's a feeling that data represents IP in a way that's just not true in data mining and machine learning research, where data sets are freely available on the internet and IP is more represented by clever algorithms you come up with. So hospitals are protective about their data and they don't want to give away something that could have a lot of value to them. Another thing is culture is just sort of institutionally. The systems in which the data is collected, digital health record systems, are actually really complex. And a lot of times getting out data of the type that a machine learning researcher would want in kind of the format that person would want is really, really hard. And I can't tell you how many times we had conversations when I was at CHLA where we'd say, we would like to get data from the ICU to analyze. And we would get this answer back from somebody who works with the database, like, okay, what data do you want? I don't know, whatever data we have on patients from the ICU. No, I need you to give me like a list of specific fields and stuff. Well, we don't know what the name of the fields are. Like, just get us everything. Here's a patient, here's his ID, just pull everything you've got for that guy. Well, I can't do that. Those kinds of barriers those are the things that I found really slowed things down, and a lot of that has to do with sort of the design of EHRs and sort of the complexity that it has to be built into them. A lot of it has to do with the fact that EHR systems, like medical records, paper records before them, are designed to capture data, but were not designed they weren't originally designed with the idea that, actually somebody's going to want to get all this data back out at sort of a aggregate level and do really detailed fine-grained analysis. Whereas when you look at companies like Google and Facebook and stuff, those are companies who I think from the very get-go, the vision was the point of getting all the data is to make it useful and analyze it. So their systems were built with that in mind and built to make it easy for them to analyze the data. Hospital EHRs were not built that way. But a lot of this is changing. So like I know CHLA is going through a lot of internal negotiations to try and bring everything together. Anybody, anywhere who's gathering data in the hospital, whether it's during treatment or for research and stuff, they're trying to find all those people and get them in the room and talk about sort of how can we put all of this together and make it easier for people to answer research questions or quality questions and that kind of stuff. But my hypothesis is that HIPAA is a convenient scapegoat to blame. And maybe for like a startup going in, there's a lot of paperwork they have to sign and that's what they perceive. But honestly, I really think it has a lot more to do with culture and like sort of willingness. Like, that if people see a lot of value in getting all that data, they will make it happen. Now, it may require a lot of work and a lot of money, but they'll make it happen. But I think a lot of times, a lot of hospitals don't immediately see what the return is going to be. It's like, how is this going to help me treat patients tomorrow? Well, it's probably not. It's probably not going to help things for another 5 or 10 years, but we have to make investments.
It seems like such a perverse tragedy of the commons to me. Like, I think at least my generation and probably other older generations and maybe even younger generations have this obsession with anonymity and privacy. And I think it's totally insane. I think people are so afraid that their insurance rates are going to get hiked. They're so afraid that their anonymous comment on a blog is going to get unveiled through machine learning and Bloom filters and stuff. But like, apparently people don't recognize the upside of this stuff. Like, just de-anonymize your information. Like, I'm so unafraid of having my information de-anonymized. Like, you want to find all the crap about me on Facebook and Google and whatever. Like, I don't care anymore. Give me the machine learning algorithm that diagnoses my illness rather than this black magic, status quo that we currently have.
Yep. That is certainly true. I think I'm kind of halfway between in that there are times when I feel protective and I don't trust a lot of the people that are gathering my data. But I think healthcare is one area where actually almost all the doctors and researchers that I've interacted with have demonstrate a real respect and a real desire to use this to create actual value, not business value, but value in terms of improving outcomes for patients and that kind of stuff. So I think this is one area where they need to work hard. It is consenting for research is an interesting thing where, if a doctor's doing like a prospective study and they need to intentionally enroll patients in a study or something like that to get their data for their research. There's kind of seems to be sort of two tribes of thought about that. One being that the hospital, the policy should be an opt-out. Like, people should sort of generally be enrolled in these studies, and then they should actually have to ask to not be enrolled in the study.
Yes.
Yeah, and that comes from a culture of fear where doctors worry that patients are dumb, and if you actually ask them to contribute their data research, they'll just say no because they're scared and they don't know what's going on. And that's an understandable thing because especially, at a place like CHLA, you have a lot of patients coming in who are not native English speakers and it's their kid who's sick. And it's just like, and then some doctor's stopping by and trying to explain that he wants to gather a kid's data. And it's like, no, I just want my kid to get better and all that. But I've met a lot of people, and I found them very persuasive, who said, you know what, no, that's our job. Like it should not be opt-out. It should be opt-in. And it should be our job to explain to patients why this is important and why they should contribute their research. And that if we work hard at that, will help create a culture where people will not be as fearful as you mentioned, Jeff, that like, their data is going to be abused, but that people understand the value and they buy into it. So I think medicine needs to work a little bit harder. They kind of need to be a little less arrogant about this and be a little more sort of open and really explaining to people, like, look at all the great research that folks at like CHLA are doing, and explain, this is going to help your kid. Maybe not tomorrow, but it's going to help kids 5 to 10 years from now if your kid participates in the study. And actually, I've been in the ICU and I've seen patients who were enrolled in like ventilator studies and stuff, and I've seen the doctors interact with the patient's parents, and like, the patients or the parents know the doctor, they know their kids participating in research, and they actually seem satisfied and proud of that. And they seem to understand, like that I was in there a few months ago. A doctor was telling me about a ventilator study, and he introduced me to the parents. He's like, "Oh, hi, I want to introduce you to, this is David. He's a data analysis guy, and we wanted to talk a little bit about sort of the study and this equipment we have hooked up." And the parents are like, "Oh, okay, that sounds great." So I actually think it's very doable, but I think the medical researchers have to work hard at it to not, and the computer scientists too, like, don't be jerks. Communicate, be open, and explain the value, and accept that some people might say no and won't be interested. But I think a lot of people, given a chance, will actually be very receptive to that. So.
Okay. Well, so I could talk about this policy stuff for days,
and you know what, dude? It's so important. The major barriers to making an impact, to sort of, when you look around and you say, why is, let's say, machine learning not making as big an impact in medicine yet as we observe in other areas, which is not entirely true. It actually is making an impact in some areas. But there's two major barriers. One of them has to do with the fact that actually it's a much harder problem, like building a model to predict disease, let's say, and deploying that in the wild is actually the bar for success is much higher there than, say, deciding what ad to show you. Because for Google or someone like that who's doing ads at a scale of millions or billions of users, as long as on average you're doing a slightly better job, you're going to make a lot of money. And if there's outlier users who don't get ads and don't click on them, who cares? In medicine, you have a much smaller scale. You have maybe tens of thousands, hundreds of thousands of patients, and the outliers are people who might die, and that's a high cost we're not willing to pay. So the bar is a little bit the metric for success is a little bit harder. The second thing, but besides that, all the barriers are not technical. The barriers are all cultural. It all has to do with like getting around the social and regulatory and other barriers that get in the way, of like, let's say we build a predictive model that we think like, wow, this seems to be able to predict sepsis 12 hours earlier than like existing things. If you want to use, it's going to be 10 years before that's at the bedside because it's going to be classified as a medical device, and now it's going to have to go through like, complex FDA process and all that kind of stuff. So those are much bigger barriers than the technical ones. The technical ones, if we could get all the data, we machine learning people, AI people could probably solve a lot of these interesting problems, or at least make things better. But they have to navigate all these regulatory and social and cultural barriers, and those are hard. It makes the upside financially much lower. Like, like you can make a startup on the web and be rich within a couple years, or you can slave away with the FDA for like 10 years and then you have to go and try and sell your thing in the hospital. So
right. Well, so, I mean, we could continue talking about these cultural barriers, but we're trying to do a show about software engineering. We want to help these people create models to serve better ads to people with their Silicon Valley startup. We're less concerned with the changing the healthcare system on Software Engineering Daily. Yeah. So, but with that in mind, I mean, okay, so you mentioned there has been some significant progress in terms of how machine learning, data science is helping healthcare. What is the current state of? I mean, are you talking about on the level of diagnosis, or what exactly? Where is machine learning actually improving healthcare?
So I think a couple of things. One area in terms of research, and my bias is certainly going to be much more towards, since I've been in academia for a couple of years, my bias is going to be toward sort of, when I think about this, when I go to answer this question, my thoughts are often going to be about, oh, I know this professor's doing this really great work. But like a good example is several labs at Massachusetts Institute of Technology, MIT, led by professors like Pete Solovich and John Gutag. These guys have been plugging away on these problems for like 20 years now. Like even back into the 80s, they were doing things where they were using machine learning to build predictive models for problems ranging from like detecting irregular heartbeats to predicting sepsis and other kinds of diseases that might develop during a hospitalization. And they've had a lot of success in building models that they can show beat sort of things that are deployed in standard like a Philips monitor or something like that. And as I mentioned, a lot of times the barriers that they run into is they go to Philips and say, I have this new model, you should buy this. And Philips says like, nah, I don't know. So there's just like, if you go and you look up like Pete Solovich or John Gutag, you can see just droves of research that those guys are doing that really is just like extremely good, solving a lot of problems, not at sort of the big data scale, but solving these very, very particular types of problems related to irregular physiology in the like the ICU or in the hospital. So a good example, I actually think that doesn't necessarily sort of at first glance may not seem like machine learning, but if you think about sort of everything that went into it, you realize like this is like the same set of tools that machine learning people do, is severity of illness scoring in the pediatric ICU. This is something that my CHLA boss, again, Randall Wetzel, was involved in. They have a score called the PRISM-3 score. That's a pediatric risk of mortality score. And the purpose of this score is to enable doing performance metrics standardized across hospitals. So the main measure of performance in pediatric ICUs and ICUs in general is mortality rate, i.e. what fraction of your patients are dying. The intuition being if a higher fraction of your, the more of your patients who come into your ICU and die, the worse you're doing. There's a problem, however, with that as a metric when you're comparing one hospital versus another. And that is that mortality really depends not just on the performance of your ICU and the treatments the patients receive, but also on like just how sick were they to begin with. And in particular, what you see is a hospital like CHLA, for example, a large urban hospital, is going to receive a lot of like the most sick patients because it's in a large urban area with a really diverse population, but also it is sort of it's like a regional center of excellence. So if at sort of satellite regional hospitals that are like, maybe 3 hours into the Inland Empire, if they have a really sick kid comes in and they rapidly realize like this is kind of, I don't think we have the expertise for this, they put them on a helicopter and they send them to CHLA. So CHLA gets a much sicker sort of base population than other hospitals. So there's a good chance its mortality rate is going to be biased by that and maybe be biased in the higher direction. So one of the things that people have come up with is they try to build mortality risk models, essentially a predictive model predicting the probability, quantifying the probability that this patient is going to die. And they do it based on measurements taken very, very early in the patient's stay or at time of admission. The idea being that measurements taken within, let's say, the first 12 to 24 hours, and in particular measured before treatment has begun, do a reasonably good job of quantifying sort of how sick is this patient when they arrived at the ICU. And so if we can build models that do a pretty good job of predicting mortality from just those early measurements, we can sort of reasonably argue that what that model is doing is it's quantifying essentially the just how sick is that patient with respect to their risk of dying. Then what you can do, if you have a model that you validate and you show is pretty good, you can take that model and you can apply that to any given hospital and say, what is your predicted mortality rate in your over the last year, when we apply this model, it predicts that 10% of your patients would die. And then we can look at your actual mortality rate and we can create something called a standardized mortality ratio that's saying that, oh, look, 8% of your patients died. The model predicted 10, so your ratio is 0.8. Hey, that's pretty good. And the general idea being that if your ratio is less than 1, you're doing a good job. If your ratio is greater than 1, you're doing a bad job. And then what you can do is if you can create a large national database, you can actually build a really good model, and then you can give hospitals like regular reports comparing them to other hospitals and giving them suggestions about things. You can start to investigate and find out the places that are doing well, that have good ratios. What kinds of policies do they have that the places that are doing bad don't have, and what can they do to try and improve?
Fascinating.
Engineers love automation, and Wealthfront automates your investing. As a software engineer, there are certain processes that you want to execute no matter what, like integration tests during a build. You wouldn't execute integration tests manually. You would use a continuous integration tool like CodeShip or Jenkins to automate your integration tests. Wealthfront is a tool to automate investing. Just like a continuous integration tool runs your tests automatically, Wealthfront can reinvest your dividends automatically and perform tax loss harvesting automatically. To get your first $15,000 managed by Wealthfront for free, go to wealthfront.com/sedaily and get started with Wealthfront's layer of automation on top of your portfolio. Wealthfront.com/sedaily. Check it out. It would support Software Engineering Daily, and you will get $15,000 managed for free if you sign up. Automate your investing. Get back to the things that you can't automate, like writing code.
So I want to get into talking about your recent work. You recently worked on a paper called Learning to Diagnose with LSTM, Recurrent Neural Networks.
Right.
And this paper you wrote focused on time series data that exists in the intensive care unit.
Uh-huh.
What types of data are present in the intensive care unit?
So all kinds. The intensive care unit is it's sort of a level of care that's halfway between the general hospital wing and the emergency room. And it's if a patient comes in and they're in imminent risk of dying, they will go to the emergency room. And if the patient is sort of, has no immediate risk, they would go to sort of be admitted to like the normal hospital. The ICU is where your condition is fragile, and their focus is on either stabilizing you or closely monitoring you to make sure that you don't deteriorate. And so this is where you actually get the highest level of measurement, because in the emergency room, they have to act immediately to try and save your life, so they don't have time to hook up a bunch of things. ICU, they do have time, and so this is where you get a lot more sort of like intubation, a lot of like physiologic monitoring, those kinds of things. It also happens to be the place where you have the highest caregiver to patient ratio, so you have the most surveillance in terms of human beings treating and monitoring the patient. So you get all kinds of things. When you think about House MD, the old TV show, and you think about the patient sitting in bed with a whole bunch of things hooked up to them, that's intensive care. So you're getting waveforms coming off bedside monitors with like heart rate, respiratory rate, other things like that. And when you have waveforms, you can do much more complex things like look at heart rate variability and look at sort of the shape of the QRS complex. But also you get all kinds of charted data from nurses and doctors, so hourly vital signs, any lab tests that are ordered where they draw blood and then measure your pH and your glucose and things like that, go into the patient chart. You could, in principle, you would have notes and other assessments by doctors. So it's basically just about every possible piece of data that you could imagine a hospital measuring could, in principle, be gathered in an ICU.
Okay,
genetics.
So
no genetics. We don't have genetics yet.
Right, not yet. Yeah. Hopefully, Theranos is not a sham.
My fingers are crossed, man. I know,
seriously.
Cool, yeah,
it really is in theory.
So in my paper in particular, out of the data that I just listed, there's a couple things we don't use. We aren't using the streaming vital signs coming off of the bedside monitor. And that's because that data, while obviously, you sort of see it and it's sort of what you think of, it's actually not routinely collected by most hospitals.
Okay. So I get that there's like tons and tons of data. So I want to get to the goals of the paper. So
sure.
Learning to diagnose with LSTM, recurrent neural networks.
Yes.
What were your goals in writing the paper?
Okay, so the primary goal, if I may be facetious for a moment, the absolutely primary goal as a PhD student was to try and publish this paper before anyone else did this, because there was a short window I realized over the summer where I was like, some people have done recurrent neural nets for sort of different types of health time series, but nobody has done it on actual sort of these modern EHR time series coming out of a hospital. And I knew other people were going to try it or were actively working on it, and I wanted to be the first to do it. So to be cynical for a moment, that was our primary goal. Zach,
well, you dodged the scoop.
Yes, that's right. Yes. Even if it doesn't get accepted, it's currently under review at ICLR. I think it hopefully will get accepted, but even if it doesn't, it's out there now, so we dodged the scoop. But the more general goal is I've had a growing feeling over the last couple of years that deep learning seems like it should be a really good fit for medicine, modulo some concerns about interpretability and things like that. In that the things we want to model, especially in physiologic time series like I'm working with from the ICU, are incredibly complex. We know sort of the underlying physiology is really complex, and that what we're really trying to model are latent disease processes. We know we have these measurements of heart rates and blood pressures and things like that, but really those are just observable symptoms of some underlying pathophysiology that has to do with sort of like systems shutting down or going wrong and things like that. And when you start talking about sort of complex problems like that, that sounds like a deep learning problem. It sounds like a perfect deep learning problem. Like we want to learn a latent space representation that captures and disentangles the correlations that we see in our actual observed measurements. And recurrent neural nets are they're really such a powerful and flexible architecture. I mean, they're in terms of sequential models, recurrent neural nets are not the only choice. There's a lot. They're whenever I do talk about related work in this area, I can list like at least half a dozen different approaches that other people are trying in this general space. Gaussian processes and subspace clustering and Bayesian models and dynamic Bayes nets and just time series mining, that kind of stuff. But what recurrent neural nets give us is this real sort of like, one, we don't have to encode prior knowledge like you would if you need to do feature engineering or if you want to wire together a dynamic Bayes net and you need to try and build in sort of knowledge about physiology, like this equation determines sort of your blood pressure based on this thing. Neural nets, we don't sort of assuming we have enough data to actually learn something, we don't need to do that with a neural net. They can capture long-term dependencies in time series, and that makes a lot of sense in health, where our intuition is that we really want to sort of capture interactions between sort of what do you look like at time of admission, and then what do you look like sort of shortly after treatment begins, and then what do you look like?
Okay, this is important. So I want to take a small detour here. Could you define the term long-term time dependency?
Okay, sure. So a long-term time dependency is, I think sort of, like technically speaking, anything in terms of classic time series models. A long-term time dependency is anything that's kind of beyond whatever sort of assumptions, conditional independence assumptions your model's making. So like a classic time series autoregressive model where you're predicting the next time step. So like, let's say the next heart rate the patient has based on some immediate history. Usually you have to define a fixed window. You have to say, okay, I'm going to predict it based on the previous 12 hours. I mean, 12 hours is a pretty long dependency, but you could imagine dependencies that actually are much longer than that go beyond the window of your model. And a model that makes a fixed window assumption like that is not going to be able to capture dependencies beyond its window. And nearly every time series model must make assumptions of that type. It's called a Markov assumption. It's assuming that, like, conditioned on this immediate history, the next time step or the thing I'm predicting is independent of anything, in the distant history.
Okay, so we have some recognition of why recurrent neural networks are helpful,
Yep.
what the importance of a long-term time dependency is. Let's think about a type of prediction, whichever you prefer: diagnosis, length of stay in a hospital, mortality, whatever you want. How could an LSTM be used for this type of prediction? Walk me through an example of building an experiment.
Okay, absolutely. So, because the purpose of our project, this is like a proof of concept. The purpose of our project was to sort of just figure out, can we actually discover meaningful signal in the data? Like, can an LSTM be used to solve a relatively, quote unquote, simple problem in this space? So the problem we posed in our paper was, the name of the paper is Learning to Diagnose. That's kind of for the lay audience. The problem we're doing is better called phenotyping. Phenotyping is a problem. A phenotype is basically an observable characteristic related to the health of an organism. That's sort of the clinical definition. Phenotyping, the way people use the term in biomedical informatics, can really just be thought of as classification. In other words, I have a patient. Here's everything I know about the patient. I want the classifier to answer the question, does this patient have this disease? So it's a little bit different. It's not predictive modeling in that there's not a temporal aspect. We're not trying to do early diagnosis or something like that. We're just feeding in. What we're using the LSTM for is, based on everything we recorded about a patient in the ICU, we want to feed all of that in. And at the end, we want the model to just tell us, does this patient have septic shock or not? Or did this patient have septic shock at some point? There's some funniness about the temporality.
Is this synonymous with the optimization objective?
You can think of this as being it is an optimization problem in that the objective function of the loss function of this thing is the predictive loss. So we know a true label. We know this patient has a disease or not. And then we're asking the model to predict, the goal of the model is to assign as high a probability as possible to the disease that the patient actually have. So we are optimizing that. That is our objective function that we are optimizing. If you mean optimization in the sort of the sense of like, kind of more of a operational thing, then I think it's a little different from that interpretation. But so this is in machine learning parlance, this is a classification problem. Given a patient object, feed it into the statistical classifier, and the classifier will just tell us. In the paper, we do 128 different ICD-9 codes, diagnostic codes. Just tell us for each of those codes, what is the probability that this patient received that code for this stay? So it's just a straight up binary classification problem. The benefits of the LSTM as we saw them would be, first of all, LSTMs and sequential models in general can handle variable length objects in ways that sort of standard machine learning models, such as a logistic regression or a decision tree or a neural network, cannot handle. We have patients. Some patients had lengths of stay, had episodes that lasted 12 hours. Other patients had episodes that lasted 3 months. And that is the kind of thing where if you wanted to apply a standard model, and we do this as some of the baselines in our paper, if you want to apply a standard model like a logistic regression or a neural net, you have to do something to produce a fixed length representation, a vector of features for each of those patients. And that's something that's just a little dissatisfying when you have these some patients have 12-hour lengths of stays and some of them have 3 months. You can imagine inventing a bunch of features like the minimum measurement, the maximum measurement, the mean, maybe a trend, difference between first and last, etc. But there's a little bit of a latent worry that you'll lose some kind of temporal resolution if you're applying that to some patients who have short length of stay, other patients who have long length of stay. And also just the promise of deep learning in general is the idea that we don't need to do feature engineering, and that using these kinds of flexible models and using learning, if you have enough data, the model can kind of learn the features that are important. So a recurrent neural net and a long short-term memory network, LSTM, seem like a really good fit if for no other reason than because we have these variable length sequences that we want to classify. So with an LSTM, just to talk a little about software, we used we built ours out of Theano, which is this symbolic math package created by University of Montreal, and it's one of the popular frameworks for doing deep learning. It's very, very similar to the Google TensorFlow, and we're kind of, I think the sense in the community is TensorFlow is sort of the future of Theano because it's going to be much better supported and engineered because it's coming out of Google as opposed to a bunch of overworked grad students. So we'll eventually migrate to that, but we've been using Theano. So we built our own recurrent neural net out of that. You don't need to do that. There's actually lots of packages that have really good implementations like Keras and Lasagne. If you move outside of Python, you can use Torch, Cafe. I don't know if they have good recurrent neural nets, but there's a lot of packages. There's DL4J for Java. So we built our own LSTM, and basically what we do is we built a recurrent layer where what you do is the hidden unit activations, the hidden state that the model is estimating at time t is a function of the previous hidden state at time t minus 1 and the inputs at time t, where in this case inputs are what was the patient's heart rate, what was the patient's pH, etc. at this time step. And you just feed you feed a sequence of measurements into the model, and then what it will do is it'll create hidden state activations at each time step for that sequence. And so what an LSTM layer will give you, given let's say 24 hours of measurements, a sequence of length 24, it'll spit out a sequence of length 24 of hidden state activations. And then what we would do to do classification is we would take the hidden state activations at the last time step, and that would be fed into like our output layer, which is like essentially a one layer neural network or something like that. And so this is actually a fairly the inner workings of a long short-term memory network are quite complex and look kind of crazy when you look at the diagram of it. And it's not the kind of thing you'd actually want to build by hand, like actually try to code in the gradients. Using something like Theano will do the gradients for you, which makes it much less likely that you'll screw it up. But the model conceptually is really, really simple. It's a sequential model that you can feed one measurement in at a time, and it will update the internal state, its estimate of the state of the system for each observation you get. And then you can use those hidden state activations to do any number of things. In our case, our task was classify the entire sequence based on the hidden state. But you could imagine also, you could use those hidden states to try and predict the next time step. You could imagine using a model like this to, like one thing we've talked about doing that we'd have to find data to do this is we'd love to feed in a sequence of measurements and then generate a clinical note. Like what note might the doctor write about this patient given this set of measurements? That looks a lot. That's just like what people have been doing for. Can
you read the note after it gets output?
I don't know. The hope is you should be able to. When you look at so like my collaborator on this, Zach Lipton, I should mention him from UC San Diego, who really deserves a lot of the credit for this work. He is sort of at the start of the fall, he was the recurrent neural network expert, and I basically recruited him. We're friends, and I was like, dude, let's do this project. You knew RNN, so teach me and let's do this project. So he has another project that he recently did where he trains a recurrent neural net to generate beer reviews based on data they scraped off of Beer Advocate. If you feed it in a type of beer and a star rating, it will generate a natural language review that somebody might write for a beer of that type with that score. And when you look at those reviews, they are uncanny. You can tell, I'm not sure this was written, it's like there's something a little awkward about it, but they are really impressive and it really captures a lot. So if we had enough data, like I think we'd need a lot of data. We would need like millions of examples, which I don't know if it'll be a long time before you could get millions of patient examples. But if we had 1 million ICU time series paired with notes the doctors wrote, I think you could probably train a recurrent neural net to take in those measurements and sort of reproduce or predict what type of note a doctor might write. Now, to the question of whether it would actually be readable to a human, probably not, because doctors write garbage. But
that was the joke. I was wondering whether you got it.
Yep.
Okay. Well, so I want to start navigating towards the close of this conversation.
Sure.
So, what were the results of the experiments?
So the results of the experiment were the meta conclusion was, yes, a recurrent neural network can discover meaning. This is really weak and not that exciting of a conclusion, but I think this is the most confident thing I would want to say about this. The recurrent neural network can discover meaningful structure in these clinical time series. When we compare the classification results across these different diseases with first, linear baselines, it clobbers linear baselines, even with hand-engineered features. When we compare it with a multi-layer perceptron trained on, which is just a multi-layer neural network trained on hand-engineered features, it also beats that. It doesn't clobber it, but it beats it. So the sort of intermediate conclusion is, aha, this worked. This is a line of research pursuing because this model can work and because it has so many of these wonderful virtues. Because there's a lot of problems we didn't solve in this paper related to irregular sampling, missing data, bias in measurements, noise, et cetera, that with enough data in principle, a neural network or a recurrent neural network probably can handle. You would not want to use this thing to diagnose patients yet. It's certainly not ready for prime time. But I believe that a model based on this architecture with sort of the problem formulated properly and with sufficient training data could eventually we will be able to build a recurrent neural net based diagnostic model that can actually be able to support doctors in making good decisions, and make better decisions, maybe identify diagnoses early, predict patient deterioration, those kinds of things. I'm very bullish about these models. I think that they will be able to work.
So zooming out, we've done several shows about deep learning. I've been reading about deep learning a lot lately. Cool. Do you think deep learning is overhyped right now? Or if it is, what is the axis on which it is overhyped?
Oh, that's a good question. Yes, I definitely think it's overhyped. You can put me in the camp of people that are deeply worried about not deeply, but that are latently worried about another AI winter, based on sort of the way things are getting hyped in the media about deep learning. Nonetheless, but I think the axis along which it really is getting hyped is sort of the intelligent machines are right around the corner. No disrespect to Ray Kurzweil and those guys, but they've been predicting the singularity is 20 years down the road for 40 years now, right?
Yeah.
They just keep moving the horizon of that. I think I'm put me more in the Andrew Ng camp of I don't think to claim that we can use a deep convolutional neural net trained on millions of images to do quote unquote human level object recognition, to go from that to we've basically built artificial brains at this point. No, I think most deep learning experts would agree deep learning is loosely inspired by the way the brain works, but really is not a plausible model for how brains actually work. And that the successes of deep learning are coming in these really, really narrow verticals, these very, very specific tasks like image recognition, speech recognition, machine translation.
What are the commonalities between those narrow domains?
Really, lots and lots of data. A very, very well-defined specific problem that is clearly solvable, and that the structure of the data and the nature of the problem lends itself to deep learning. In particular, when you look at sort of one of the things that sets medicine aside from medicine slightly different from text and image data is image data is homogeneous in the sense that the input is a bunch of pixel intensities, and And the kinds of features that you'd want to learn to build like a good image classifier tend to be like sort of detecting patterns within those features. Same thing is true of text. It's homogeneous data. You have like words that end up getting encoded as like vectors of some type, maybe like a one-hot encoding or something. Same thing for speech. You have this sort of homogeneous data, and it's really sort of patterns within that homogeneous data that are important. Medicine, there is this sort of question of like, we have heart rates and blood pressures and pHs and other things that have these very, very different distributions. And it seems somewhat different in some sense. But I think the main thing is just massive amounts of data, massive amounts of labeled data. Like when you look at sort of where are these things actually not just interesting from a research standpoint, but really are like, if you're going to build a speech recognition system to be deployed on a phone to allow people to search for things, like you would want to do that based on deep learning. Why? Because you can get tons of data. Like you can just get lots and lots and lots of labeled data. And if you have lots of labeled data for a very doable task, a neural net will be able to do it. Like, if you can find the right architecture, you will be able to do it. So,
well, presumably the world is getting increasingly schematized. So maybe that is the line that will go parallel with us having increasingly human-like systems, perhaps.
Well, I think the things that are most interesting from that standpoint in the deep learning world are two lines of work. The work on deep reinforcement learning. So like the work coming out of Google DeepMind, where they're training systems to play video games, and these are systems that where like the input to the thing, the input to the deep reinforcement learner is just like a screenshot, is pixel intensities, and they're not giving it any kind of prior knowledge about the game or how the game works or the structure of the game. They're not building in any kind of game specific knowledge in any way, shape, or form. They're literally just feeding this thing screenshots of the image, giving it control, allowing it to fiddle around with the controls, and then giving it sort of some kind of end objective, like you won or you lost or this was your score. And these things are learning to actually be able to play games, in some instances better than people. That's pretty damn impressive, and that's really, really interesting. The other thing is the work on these sort of memory networks or neural Turing machines, where they're hooking up a recurrent neural net to some kind of classic computer science data structure like a stack. And what you're seeing, there's recent work out of Facebook AI where they trained one of these systems they trained it on the Lord of the Rings and found it was able to answer basic reading comprehension questions about the Lord of the Rings, like, who was Sam with on the stairs of Cirith Ungol? And the thing would respond with Frodo. And not only would it say Frodo, but it could actually retrieve passages from the book. Say specific sentences where it actually talks about Sam and Frodo on the stairs of Cirith Ungol. And what you saw is this thing has some ability to actually memorize. At the same time, it's using the neural architecture to do pattern recognition. It's using these external memories to actually memorize facts, to write down things. Both of those things are pretty, like, that's starting to look like types of, human level types of behavior, which is pretty interesting.
Absolutely.
Yeah. So I'm really excited about them. I think we have to be careful about overhyping them. I think the profound question within academia is, deep learning is clearly hot. The question is this a fad that will go away the way it did in the 90s, where like eventually we found, SVMs with kernels are better than neural nets at that point? Is this yet another fad where neural nets have gotten ahead of other techniques, but then in 5 or 10 years somebody will invent some other technique that will actually do just as well as a neural net, and it won't require nearly as much data or training, and so people will want to use that instead because it's easier to use and computationally efficient. So the question is, will that happen, or are the progress and the strides that deep learning have made, is it here to stay? Essentially, in speech recognition, any future speech recognition system will use deep learning in some form or fashion. Maybe deep learning will just be sort of become a commodity component, and the real insights that let you get the next breakthrough won't have anything specifically to do with deep learning. But deep learning will be an essential piece of that system. I'm willing to, if I had to bet money, I'd say it's the latter. I think there's areas where deep learning is just here to stay. So.
Fascinating. Well, that sounds like a great place to close off. David, I really appreciate you coming on the show to talk about your recent work and your macroscopic view of where deep learning is taking us. Appreciate you coming on Software Engineering Daily.
Yeah, thank you for having me. I was really excited to hear from you. I like talking about this work and evangelizing this stuff. And I think deep learning is a cool thing. And unlike a lot of pieces of machine learning, parts of machine learning, it's very much empirical, and you can get really good at it through trial and error and developing an intuition for what works. So it's something that I think, for folks out there who are interested in it, who don't have time to pursue a PhD, there's no reason why you can't turn yourself into an expert on this stuff. So I highly encourage people to check it out and play with it.
That's great. Well, thanks for coming on the show, David.
You bet, man.